Now that I've introduced the concept of sequential programming, let's evaluate the pros and cons of this particular programming paradigm. As always, overcoming these cons motivates our focus on the concurrent and parallel programming techniques in the Java and Android platform, which forms the basis of the actual course. So this is still kind of just the background, the baseline, if you will. So let's start off by talking about the pros, or the good things of sequential programming. First and foremost, the sequential program is relatively easy to program and debug. Relative is the key word here. Obviously, you can have incredibly complicated sequential programs because of the complexity of the algorithms involved, or just the complexity of the implementation techniques that are used. Compared to concurrent and parallel programs, however, a sequential program is typically easier to program and almost always easier to debug. So why is that? Well, one reason is because typically in a sequential program, especially one that's well-written, especially one well-written using patterns, often is intuitive because the program matches the steps that are expressed in the algorithms. So here's a very simple example of an algorithm that you're probably familiar with, which is selection sort, which is a very simple sorting algorithm that takes an array or a list and it marches through the array or a list from start to end. And every step along the way, it selects the item that's the lowest if you're doing an ascending sort, or highest if you're sorting in descending order. Let's do ascending order to make it easy. It selects the lowest item, puts it at the front of what it's considering, and then goes on and does the same thing with the next item as the new beginning. And if you look at the code here, it's relatively straightforward to understand. And the nice thing about this sequential code is there aren't surprises lurking here. You can read this algorithm just by looking at it. It forms a linear sequence of steps, and there aren't surprises that will come to plague you. You might ask, what kinds of surprises are you thinking about here? Well, these are surprises that typically confer or are typically related to concurrency hazards or parallelism hazards, like race conditions, memory inconsistencies, and so on. And we'll talk a lot more about that as we get further along. But this code is nice because there really aren't any surprises. Another way in which sequential programming is relatively easy to program and easy to debug is because the behavior of the program in the debugger is quite an accurate reflection of the actual program behavior. You're doing an apples to apples comparison, if you will, between what your program does and how it's performing in the debugger. Unless, of course, you have some kind of weird real-time system, which we're not going to talk about right now. In contrast, the behavior of non-sequential programs, be they concurrent or parallel or whatnot, often differ when they run in the debugger versus when they run in the wild. In other words, without running in the debugger. And the reason, of course, for this divergence is because there's often perturbations in timing in the different execution contexts. So when you run in the debugger, some threads, typically the thread that you're stepping through, will be running in a different time frame than all the other threads that are not running in a single step as part of the debugger process. And that may not be the way things would behave if you weren't running in the debugger. So you'll get all kinds of different variations in the timing in which things run, which will cause all kinds of strange problems. Now, needless to say, there's other issues with concurrent and parallel programs that cause problems for debuggers as well. But this is just one simple example where debugging will change things in concurrent and parallel programs in ways it won't in sequential programs. Another benefit or pro of sequential programming is deterministic execution order, which helps to simplify reasoning, either our reasoning as developers or students, or static and analysis tool reasoning about the behavior of the program, and more importantly, the assuring of the program behavior. And this assurance, making sure things work properly, that they happen in the right order at the right time with the right output and so on, is especially important for safety-critical cyber-physical systems. These are systems like medical devices, driverless cars, the power grid, airline, traffic control systems, airplane flight control systems, various kinds of power plants or various kinds of chemical plants or process control environments, wind farms, scientific experiment laboratories, you name it. In all these environments, the right answer delivered too late becomes the wrong answer. And so in those environments, it's often very important to have deterministic behavior. And sometimes that means using very primitive or very traditional programming techniques and programming tools. So you might end up using single-threaded code. You might end up using single core processor. You might end up turning off any caches that the processor might have. You might stick with sequential code and so on. So in some environments, especially the ones that are really safety critical, we still limit ourselves. However, almost everything else that we talk about doesn't work that way. And so all the stuff we're going to talk about later in terms of concurrent and parallel programming is quite relevant and very germane to modern practices in software development and software assurance. Naturally, not everything is unicorns and rainbows. There are cons of sequential programming. One of the biggest disadvantages, of course, is we can't leverage the parallelism available in today's multi-core systems, which comes to us courtesy of Moore's law, where there's more and more transistors. So people keep adding more and more cores to our chips that we use. And if you're doing sequential programming, then that program by itself may or may not, most likely not, be able to access and leverage the parallelism on a multi-core environment. As a consequence, performance, which can be looked at in terms of throughput, scalability, latency, or whatever, may suffer relative to alternative concurrent and parallel programs. And here's a simple little chart that shows this. We see on the right hand, or the x-axis, we see the number of physical cores from 1 to 48, which would be pretty aggressive. 48 core, there are not a lot of single chips that have 48 cores at this point, but most of them nowadays are 4 to 8 to 10. My MacBook Pro has a 10-core processor, which is really cool. And then that's the number of physical cores. And then we see the running times of various kinds of programs, sequential programs, concurrent programs, and parallel programs. The main thing to note here is that as the number of cores increase, your performance of sequential programs is not going to go up any, or if any, it goes up infinitesimally small, probably won't go up any at all. Whereas concurrent and parallel programs are better. They scale better. We'll talk later about the difference between concurrent programs and parallel programs. The running time here really is how much work you can do per unit time. So you can obviously do more work with a parallel program on a 48-core machine than you can do in a parallel programming environment on a single-core machine. So that kind of illustrates the types of performance speedups we're talking about. Other cons of sequential programming is it can often be hard to program a sequential program to be responsive to multiple sources and sinks of input and output. Examples of such sources and sinks would be mouse movements, mouse clicks, touch events, GPS location signals, network connections, asynchronous reads and writes that may occur in a file system, be it a disk or some other media like a flash drive and so on. And in those environments, a single thread of control can be difficult to coordinate access to many sources of input and output, and sinks, sources of input, sinks of output. And as a consequence, your program is often going to be ugly and difficult to write, difficult to debug and maintain. And those are things that will, of course, motivate concurrent and parallel programming. The reason why it gets complicated is having only one thread of control that has to keep track of lots of different things leads you to a somewhat awkward event-driven programming style where you have to sort of neurotically and compulsively pull a bunch of sources and sinks and split the work up into little chunks and try to keep track of all the events. And it just basically partitions things in time and space that are hard to reason about. We'll talk later about a more modern way of handling this type of programming using so-called reactive programming styles, which help to solve this problem in a much more fluid and fluent way. Needless to say, overcoming these cons, inability to leverage parallelism in multi-core systems, hard to be responsive to multiple I/O sources and sinks, that's what motivates the concurrency and parallelism topics that we're about to go into much more detail about. So that's the end of the overview of the pros and cons of sequential programming.